Welcome to Quantum. Today, in this presentation, we'll provide an overview of the Sachdev-Ye-Kitaev (SYK) model and its connection to Sachdev-Ye-Kitaev (JT) gravity. The SYK model is a quantum mechanical model that has gained significant attention due to its role in describing holographic principles and quantum chaos. The SYK model originates from condensed matter physics, where it was initially introduced to describe a system of interacting fermions. However, it quickly became significant in the context of high-energy theoretical physics because of its connections to holography and quantum gravity. Holography is a principle that suggests that the information about a volume of space can be described entirely by its boundary. In particular, the SYK model is believed to describe the physics at the boundary of a two-dimensional anti-de Sitter, a DS2, black hole, a specific type of black hole geometry. The SYK model's link to holography is largely due to its behavior in the infrared IR limit, where it displays conformal symmetry. This conformal symmetry is also present in the Sachdev-Ye-Kitaev JT gravity model, a two-dimensional theory of gravity. Both the SYK model and JT gravity share the same symmetry in the IR limit, and their dynamics are governed by the same effective action, the Schwarzian action. This connection makes the SYK model a candidate for the field theory that lives on the boundary of an ADS2 black hole. A fascinating property of the SYK model is its maximal chaos. Like black holes, the SYK model reaches the upper limit of chaotic behavior, as defined by the Maldacena-Schenker-Stanford MSS, bound on the Lyapunov exponent, kappa equal 2 pi over beta, where beta is the inverse temperature. This chaos is measured by out-of-time ordered correlators, OTOCs, which show how information scrambles throughout the system over time. Maximal chaos is closely linked to the concept of fast scrambling, which refers to how quickly information spreads through a system. In both the SYK model and the ES2 black hole, this scrambling of information is measured using out-of-time ordered correlators, OTOs. These correlators tell us how two initially commuting operators become non-commutative over time due to interactions. Essentially, they provide insight into how quickly information spreads and gets mixed up in the system. At its core, the SYK model consists of n-Majorana fermions interacting randomly with each other. Despite the randomness, the model is solvable in the large n limit. It's closely connected to tensor models, which are solvable at large n and provide a bridge between simpler vector models and the more complex matrix models. In summary, the SYK model gives us a powerful way to study the relationship between quantum mechanics, chaos, and gravity. Its solvability, emergence of conformal symmetry, and connection to black holes make it a crucial model in modern theoretical physics. Now, we're going to explore large n quantization in the Sachdev-Ye-Kitaev model, where the number of fermions n becomes very large, allowing us to simplify and solve the model. This process involves the effective action and the Dyson-Schwinger equations, which describe the dynamics of the system. The degrees of freedom in the SYK model consist of n-Majorana fermions, denoted as chi-I, where I ranges from 1 to n, which satisfy anti-commutation relations, as shown in equation 1. In the SYK model, these fermions interact through random, all-to-all couplings represented by JIJKL, which are drawn from a Gaussian distribution with a zero mean, as described in equations 2 and 3 and 4. The SYK action is presented in equation 5. The first term represents the kinetic energy of the fermions, while the second term describes their random interactions. The corresponding Lagrangian and Hamiltonian are given in equations 6 and 7. The computation of the effective action, which simplifies by averaging over the random couplings, is shown starting from equation 8. The partition function in equation 12 is then further expressed in terms of the bilocal fields G and sigma, which act as the exact propagator and the self-energy respectively. The end result of the partition function is equation 18, with the effective action S effective given in equation 19. The Dyson-Schwinger equations are then obtained by varying the effective action with respect to the bilocal fields G and sigma. These equations, which are given in equations 21 and 22, essentially tell us how the system evolves. The propagator G starts with the free propagator G0 and is then modified by the self-energy sigma, which accounts for the interactions. In the large N limit, the system's behavior is dominated by melonic diagrams, as described in equation 25. These diagrams are the leading contributions in the large N expansion, and they simplify the calculation of the Green's function. For instance, the correction to the free propagator G0 due to interactions is dominated by the first melonic diagram, as shown in equation 26. Now, we're going to explore the emergence of conformal symmetry in the SYK model. This is where the model's behavior simplifies even further at low energies, revealing deep connections to conformal field theories, chaos, and holography. In the infrared IR limit of the SYK model, where N is large and the energy scale is much smaller than the interaction strength, the system reaches strong coupling regime. At this point, the kinetic term becomes negligible compared to the interactions, simplifying the system dramatically, as described in the simplified Dyson-Schwinger equation 40. This equation exhibits time reparametrization symmetry, which means that the system is invariant under transformations of time itself tau, where time is reparametrized by an arbitrary function f of tau. The propagator and the self-energy transform under this time reparametrization accordingly, as shown in equation 44. In this limit, the system's propagator follows a power law behavior, reflecting the system's emergent conformal invariance, as shown in equation 42. This conformal symmetry means that the system behaves in a way that is invariant under scale transformations. The propagator decays as a function of time in a specific way, controlled by the scaling dimension delta. For the SYK model, this scaling dimension is found to be 1/4, as shown in equation 46. The final result for the exact propagator in the IR limit is then given approximately by the conformal propagator GC, given in equation 49. In the low-energy IR limit, the SYK model exhibits therefore reparametrization invariance, which is precisely conformal symmetry in one dimension, which is captured by the conformal action SCFT in equation 59. The effective action S effective contains also a non-conformally invariant part SI, given by equation 60. The addition of this conformally non-invariant action SI, which corresponds to the inclusion of the kinetic term, will lead to the spontaneous breaking of the conformal symmetry of the action SCFT, which induces as a consequence Goldstone modes given in terms of a scalar field f of tau, which is precisely the time reparametrization function of the conformal symmetry. These soft reparametrization modes are governed by the so-called Schwarzian action, which captures the low-energy dynamics of the SYK model. In essence, small perturbations to the conformally invariant system are governed by the Schwarzian action. To construct the Schwarzian action, we start from the observation that the solutions of the Dyson-Schwinger equations are given by a manifold of vacuum states obtained from the conformal propagator GC by the action of the reparametrization transformation f of tau. In other words, there is in fact an infinite number of solutions GF of the Dyson-Schwinger equations which are parametrized by the function f of tau and which all have the same conformally invariant action SCFT. Equation 67 show explicitly the additional solutions of the Dyson-Schwinger equation which are connected to the conformal propagator by the action of the reparametrization function f of tau. Whereas equations 73 and 74 show the condition satisfied by the conformal fluctuations delta G. These fluctuations are therefore modes of the conformal kernel K with eigenvalue 1. Finally, equations 75 through 78 show explicitly the invariance of the IR conformal action SCFT under conformal reparametrization transformations. The variation of the effective action around the conformal solution is therefore given by the variation of the kinetic action SI only as shown in equation 79. This in turn is given in terms of the fluctuation delta G, which is given in detail in equation 81. The result is given in terms of the so-called Schwarzian derivative defined in equation 84. The final action, equation 85, is precisely the Schwarzian action. Thus, by choosing a particular reparametrization function, f of tau, at the level of the Schwarzian action, the original conformal symmetry of the theory is explicitly spontaneously broken down to an SL2R symmetry group. These results can be extended to finite temperature using the conformal map relating the line and the circle given in equation 88. In this section, we discuss the four-point function of the SYK model, which plays an essential role in understanding the chaotic nature of the model. The four-point function is defined in equation 94. In the SYK model, there are three key contributions to the four-point function: the disconnected tree-level result, the connected contributions due to the Schwarzian soft modes, and the connected conformal contributions. The disconnected part is the simpler one. It's essentially just a product of two-point functions, as shown in equation 95. The more interesting part, however, is the connected contribution due to the Schwarzian soft modes, which arises due to interactions in the system in the low-energy region where the SYK model reaches the strong coupling regime. This is where the system's chaotic properties emerge. In equation 96, we parameterize the parallel fluctuations around the conformal solution in terms of the reparametrization function f of tau. In equation 98, we compute the Gaussian approximation of the Schwarzian action, which allows us to compute the propagator of the reparametrization function f of tau in equation 99. This propagator allows us to compute the propagator of the Schwarzian field in equation 100. The soft mode correction to the four-point function is found to be given by the propagator of the parallel fluctuations, equation 101, which can be expressed in terms of the propagator of the Schwarzian field, equation 102. The four-point function at this stage reveals two different possibilities: the time-ordered correlator, TOC, and the out-of-time ordered correlator, OTOC, computed in equations 109 and 114, respectively. It is observed that the four-point function exhibits maximal chaos in this low-energy limit, where the soft modes dominate, which can be quantified by the decay of the out-of-time ordered correlation given by equation 114. Maximal chaos of the SYK model means that information scrambles the fastest, which is a property shared with black holes. In the last subsection, we compute the conformal contribution to the four-point function due to the perpendicular fluctuations, which are orthogonal to the conformally invariant space of configurations. The answer here is given by ladder diagrams, which come in the form of a geometric series. This can be summed up to give the contribution in equation 119. This correction to the four-point function is thus determined in terms of the spectrum of the kernel K given by equation 121. This gives the conformal spectrum of the theory in equation 122. The conformal contributions to the four-point function, although they are at the same order of 1 over n, they are suppressed by the factor 1 over beta j compared to the contribution of the Schwarzian soft modes. We get similar expressions for the TOC and OTOC functions with a Lyapunov exponent satisfying the chaos bound. We conclude this presentation by referencing some of the most important articles on the subject. Goodbye, and see you next time.